One of the great tools in Blender is the Boolean modifier, and related to that, the mesh Boolean node. The only real problem with both of these is that once your meshes become complicated to any level, the speed of them can start to cause problems. And I think for a specific use case, I've found a pretty good solution. So in a project I'm working on, I wanted to do a lot of self-intersection. So that means you have a single mesh object that has a lot of overlapping geometry, and you want to get rid of that geometry. And in my case, I wanted to union those together so that any of the geometry that was inside of both of them would be removed. So let's take a look at a simplified version of this to see where the problem lies. So in this case, I've got a subdivided cube and a subdivided icosphere. I've created an object with geometry nodes. I'm bringing in the cube and icosphere. I'm moving the cube over a little bit and rotating it, but they're still overlapping. And I'm doing a join geometry on them and then sending it out. So you can see here that these are really just two overlapping meshes. They have not been fused together. Now, an easy standard practice would be to replace this join geometry with a mesh Boolean node. I'd set it to union, and I'd bring in the two objects. As you can see here, they have been unioned together. But that's when the two meshes are separate. What happens if the object that I bring in is already one mesh? So let's take these two objects and duplicate them, and then I'm just going to overlap them and do a Control-J to join them. Now this is one mesh object, and you can see, again, it's overlapping. I'm just going to name this overlap. I'll bring overlap into my node tree, and if I bring that across, you'll see that I've got the object like I wanted. If I connect this in to my mesh Boolean and hook it up there, you'll see that nothing happens. And if I turn on self-intersection, nothing happens. One of the things is, if the Boolean solver is set to float, these options don't actually do anything. You'll notice that if you use the Boolean modifier, those options aren't even available for the float or the fast method. So instead, I'm going to go over to the exact method. And by default, even with these on and off, this doesn't change whether or not it does self-intersection. It just automatically does it. So you can see here we're getting the result that we're looking for, these two objects unioned together. Now here's the problem. So if we look at this situation where I've got a mesh that has overlapping geometry, and I use the exact method and get self-intersection, it takes 178 milliseconds to do this operation. And while that's not a ton, if we were to do that a bunch of times, that really starts to add up. If we go back to the previous, where we're just taking two separate objects and unioning them with the float method, you'll see that it does it in 1.9 milliseconds. So obviously a major speed up, which would allow you to do this operation a lot of times in the time it would take you to do the other just once. The only problem is, if I join these together before they get to the mesh Boolean, once again, we've got our overlapping geometry. Or if I were to input a mesh that already has overlapping geometry and use the float method, I'm back to square one. So we want the speed of the float solver, but we also want to do self-intersection. So in playing with this and trying a bunch of different things, I did run across something interesting. The inputs for this Boolean operator treat the mesh data as one mesh, but then it treats each individual instance as another mesh to be combined with the previous. So if I go back down to this example where I'm using the float method on these two objects, but I've joined them together first, so the Boolean node sees them as one mesh. And if we look over in the spreadsheet, we can see we've just got mesh data and no instances or anything else. But as soon as I turn this into an instance, you'll see that my mesh data has reduced here. And if I add in a viewer node right here by Control-Shift clicking on this join geometry, and I look up here at my spreadsheet, you'll see that I've got mesh data and I've got one instance. So the icosphere is coming in as mesh to the join geometry, but the cube is coming in as an instance. If I turn them both on as instances, you'll see I no longer have any mesh data and I have two instances. And if I get rid of my viewer node, so I'm back to my final result, you'll see that I'm getting my self-intersection. The key here being my resultant time is 2.1 milliseconds. This is vastly better than the results we were getting with the exact method, which was almost 100 times slower. What's also interesting is if we take this approach using instances and apply that to the exact solver, it only takes 27 milliseconds. So using the float with this method is still over 10 times faster than the exact. Using the exact with multiple instances is 10 times faster than using the exact just by itself using self-intersection. So let's create a situation where we generate some overlapping geometry and see how we could make this work better. All right, so I've got something very simple here. I've just got a repeat zone that creates a bunch of cubes. And for each iteration, it just moves the X translation over a little bit and rotates it on the Z axis. So we end up with this line of cubes. If we wanted to turn this into one mesh that was all fused together, we would simply add a mesh Boolean node here. We would change the method to exact, and there we go. So now if we increase the iterations to say 20, we can see that this is taking 149 milliseconds, with the mesh Boolean taking the majority of that time. If we were to change these cubes into instances before we send them, so we could do a geometry to instance, plug that in here. First off, we see that our time drops to 109 milliseconds. So just doing that makes the exact method work faster. So now let's change that to the float solver. And you can see we've dropped to 9.2 milliseconds. That's an improvement of 10 times over the original. Now I've upped the subdivisions of the cube to 10 on all three axes. Let's see how that changes things. This took almost 6 seconds to do the entire union. Now let's check the float method. Here you can see we've run into some trouble. This hasn't solved exactly like it should. It did it a lot faster, but the result isn't exact. So you will need to check to make sure that you're getting accurate results for the mesh that you're doing. But as of recording this video, Blender 4.5 is about to come out. And let me just show you. And let me pull that over so that you can see the difference there. So here in Blender 4.5, we get the same result with the float solver. However, a new solver has been added to Blender 4.5 called the manifold solver. And since all of our cubes are manifold, which means they're all watertight meshes, it solves this a lot better. And we can see here that our solve time is 67 milliseconds. And the solve has all of the components. Now, I have noticed that the float solver will be faster than the manifold solver in some instances. In other instances, the manifold solver is quite a bit faster. You can see here that between the manifold solver and the exact solver, we go from 66 milliseconds to almost 6,000 milliseconds. And as you can see, that's almost a 100 times performance increase between the exact solver and the manifold solver for this particular setup. So, while I can't say that the manifold solver will always be the fastest, or that the float will be, or whatever, you'll need to try each one with this method to see which one works faster. Now the object that you're working on might not be generated like this, so you might not have the option of inserting a geometry to instance inside your creation like this. And you might be handed a mesh with overlapping geometry. So what I wanted to do was take a node that would take a mesh that has multiple mesh islands that may or may not be overlapping and split those islands into separate instances. Then you could feed that to the mesh Boolean node and have it do this. So let's take a quick look at how we could build a mesh islands to instances node. I'm going to get rid of this geometry to instances here, and we're just going to work on this as if this was just a mesh that was given to us or a mesh that we've loaded that we don't have the ability to already turn into instances. So let's create a group that we can reuse that later we could turn into an asset that we could add into any of our projects. So I'm just going to do a shift middle mouse drag across this to create a reroute, and then I'm going to press Ctrl G on that reroute to create a group. We're going to call this our mesh island to instances node. Now we're going to want to iterate over the mesh islands in our mesh. So we're going to need a repeat zone for that. Now we need to know how many times we need to repeat. We want to repeat once for each mesh island, so we need to grab the mesh island count. We can find that with the mesh island node, and we need to sample one of the points of our mesh to see how many mesh islands are in the entire mesh. So I'm going to use a sample index node. I'll change the type to integer, and the value will be the island count. I'm sampling index 0, which means as long as our mesh has at least one point in it, we can sample it to see how many mesh islands that particular mesh has. So this value will be the island count of our mesh. Our new output geometry that we want to create is going to start with nothing. And we're going to build up a list of instances inside this new geometry, and then that's what we'll send to the output. So now on each repetition, we want to isolate the mesh island that has the index number that's the same as the iteration. So we can get rid of the rest of the mesh that's not part of that particular mesh island. So if we do a delete geometry, we'll bring in the entire geometry. And then the part that we want to delete is where the mesh island index is not equal to the iteration. I'll take the island index not equal to the iteration, and that will be our selection. So when we're on iteration 0, it's going to say, is this point part of mesh island 0? And if it's not, it'll delete it, leaving us with just the points that are part of mesh island 0. We can now take that remaining mesh and turn it into an instance. We'll use the geometry to instance node, and then we want to join that with this loop that we're creating. I'll change my input to mesh and my output to instances. And you can see that this only took 1.6 milliseconds to complete, so this is a pretty efficient node. And if I do a viewer on it, you can see that it is full of just instances. So we can see that bringing that into the manifold solver here in Blender 4.5 beta gives us an output time of 56 milliseconds. The float solver still has trouble, and the exact solver, like we had seen before, is going to take a little while to complete. Again, around 6 seconds. Now you might be wondering why the float solver fails on this particular mesh. And the reason for that is the float solver doesn't do well when you have faces of the mesh that are exactly overlapping. Sometimes that causes it some problems. So you can see this is pretty messed up. But if we were to alter the heights of the cubes by just a little bit so that they weren't all perfectly in line with each other, that might help the float solver solve better. So let's do that real quick. What I'm going to do is just bring in a combine XYZ for the scale. I'll bring in a random value node, and I'll adjust the Z height for each one. Now, since my cube is 1 by 1 by 1, I'll make the minimum Z height 0.998 and the maximum 1.002. So it's got a little bit of leeway in each direction. Since this works with fields and scale here is a single value, I need to give this an ID so that it generates the same value for all of the points. And now you can see the float solver is succeeding. And in this case, it's taking 116 milliseconds, while manifold is taking 52. So again, your mileage may vary depending on the particular mesh that you are trying to work with. So whether you're using just the float solver in Blender 4.4, or you're choosing between the float solver and the manifold solver in Blender 4.5, so this could be a real game changer if you're doing unions like this to generate more complex meshes. Be aware that this method will give you odd results if you use the intersection or the difference methods and you have more than 2 instances in your pipeline. You might not be getting the results you want. For union, it should work with however many instances you throw at it. Anyhow, so that's it for this little exploration of the mesh Boolean node and some ways to make it more efficient. I hope you get something out of this, and I hope it inspires you to make something awesome. If you haven't noticed, I've enabled YouTube memberships for this channel, so if you'd like to support the channel, you can either do so by joining my Patreon, or you can support with a channel membership. Either way, you get access to all of the source files for my tutorial videos. Thanks again for watching, and until next time, I'll catch you later.